Hello. In this presentation, I will explain you the Black-Scholes-Merton model. The Black-Scholes-Merton model is used for the valuation of option derivative. This model is based on the log normal distribution. I will explain you the conceptual understanding related to this model in the following slides.
So in this slide, I will explain you what is log normal distribution. So firstly, I will explain you what is the difference between normal and log normal distribution. So first you look into this histogram probability distribution. In this diagram, you will see that there are two lines. So first is this blue line, okay, and second one is this green line. So this blue line represents the normal distribution and the green line represents the log normal distribution. Now, when you look into the normal distribution, which is blue line, you observe that it is symmetrical on right and the left side. So it has a symmetrical nature, the normal distribution, which is blue line. On contrary, when you look into the green line, which is log normal distribution, it is not symmetrical and it is more skewed towards right hand side. So when you look into the right hand side, you will observe that this log normal distribution is more skewed. Now, when you look into the stock prices, when you analyze the stock prices, we observe that the stock prices follow the log normal distribution. So just an example, the stock prices have random behavior. So stock prices move in a random form. For example, this is the trajectory for the stock prices movement. Now, when you transform this movement of stock prices into the probability distribution, then it behaves as a log normal distribution. So now when we analyze the stock prices using the model, so we use the log normal distribution. Okay. Now looking into the log normal distribution, you also observe that the log normal distribution do not have the negative values. It only have the positive values. And when you have the stock prices, technically, it also cannot have the negative value. It will always have a positive value. Another important point of the log normal distribution, the log normal distribution for the stock prices means that it has potential for large, which is very important point. It has a potential for large positive gains. Because of this property of the stock prices, the distribution is skewed towards right. And because of this property, the stock prices follow the log normal distribution. Okay. Now I will look into this property, potential for a large positive gain, by looking into this example. And this is very, very important. When you look into this example, let's suppose the price of the stock is 100. The current price of the stock is 100. And what I am doing is that I am doing some mathematical calculation. In one scenario, I have used the annual compounding. And in the second scenario, I have used there is no compounding. And let's suppose there is on right hand side, the prices are increasing by 10%. Okay. The prices are increasing by 10%. And on the left side, we are doing the analysis. Let's suppose prices are decreasing by 10%. So here we are applying that prices are decreasing by 10%. And what we are doing is that we are doing the analysis of what will happen if we have the compounding, what will happen if we do not have the compounding. And when I say the compounding here, I mean that we are applying the annual compounding. Okay. Now, in the year one, if I have a 10% increase, okay, so what I will do, I will multiply by this factor 1.1. Okay, 1.1. What I will do is that I will multiply 100 by 1.1, and the resultant number will be 110 and 110. That is in the year one. Now, when I move into the second year, I will apply for the compounding. I will again multiply the resultant, this is 110 by 1.1. Okay. What will be the resultant number? The resultant number will be 121 if I have a compounding. However, if I do not have the compounding, it will be 120. Now the difference here is that because of the power of compounding, my resultant result will increase. And the more I move towards right, if I move towards year 3, you will find that my resultant number, if I am applying the annual compounding, which becomes 133.1, and however, if I am not applying the compounding, it is 130. Okay. So it means that my value has increased by 3.1 in the case of compounding in comparison to if I am not compounding. Okay. So what you will identify here, what you will observe here, if I am applying the compounding, my potential for the large positive gain has increased on right hand side. Similarly, if I move towards the left hand side, here also what what we are doing here is that we are reducing the current price by 10%. So if we are reducing the current price by 10%, then we are multiplying the current price by the factor which is zero point 0.9. So we are multiplying 100 by zero point 0.9, and the resultant value will be 90 in the year 1, which is in both the case compounding and not compounding. However, the compounding effects start in the second year when I again multiply by zero point 0.9. When I again multiply by zero point 0.9, you will observe that my value because of the compounding is 81, and when I am not compounding, my value is 80. And similarly, in the year 3, you will observe that my value is 72.9 when I am compounding. So it has reduced from 100 to 72.9. However, in case of if I am not compounding, it has reduced to 70. So my potential for losses has reduced if I have a power of compounding. Because of that, on the left side, you will observe that my losses have reduced. However, on the right side, you have observed that my potential for gain has increased because of the power of compounding. Because of that, the stock prices, the behavior of the stock prices, because of the power of compounding, it is log normal. It is skewed towards right hand side. And because of this property, we use the log normal distribution to model the stock prices. And in the Merton model, we are using the log normal distribution. Now, the second property, if let's suppose the stock prices follow the log normal distribution. And if I will take the log of, suppose ln is a log of stock prices, if I take, then the resultant is equal to x. Okay. So I have already explained you the S is following this, which is log normal distribution. But if I take the log of the stock prices, which is equal to y, then it will follow the normal distribution. It is very, very important. If a stock price is following the log normal distribution, then if I take the log of the stock prices, the resultant, which is y, it will follow the normal distribution. This is very, very important. Okay. Now, this other point I will touch upon. If I have a y, I will say that if I have a st, the stock prices at time t, and stock prices at a time t is equal to, let's suppose, my current value of the stock prices, and I am doing the compounding, and I am multiplying by e to the power, which is r. R means return, return, and I am multiplying by t. So in this slide, I will explain you the assumption of BSM model. So the first assumption of BSM model is that the stock prices follows the log normal distribution. I have already explained you about the log normal distribution in the previous slide. This is the assumption of the BSM model, like the underlying asset follows the log normal distribution. And I have already explained that in the real world, the asset prices follows the log normal distribution because of the impact of the compounding. Now, if the price follows the log normal distribution, the log of the stock prices will follow the normal distribution. This is also the assumption of BSM model. So the variable that is log normally distributed is the one where the log of the values in that case are normally distributed. Okay, so what we are saying is that if st, this st is following the behavior of log normal, then ln of st is following the normal distribution. So ln of st is a normally distributed, which has a mean, which is this, and the standard deviation, which is this. S naught is the stock price at time 0, and st is the stock price which we are estimating at time t. Sigma is a standard deviation or the volatility of the stock prices, which is per year. Now, the important point here is that let's suppose if I take this ln of s naught to the denominator here, I can do that mathematically. In that case, it will have ln of, okay, st divided by s naught. This is called as the log normal return. Okay, and if this is my log normal return, because I have taken this to the denominator, then my mean will be this factor, u minus sigma square divided by 2, and my standard deviation is sigma multiplied by root t. Now, important point here to observe is that why we are reducing my mu, which is my expected return for the stock, minus of this factor, which is standard deviation of square divided by 2. The reason here is that let's suppose if I have a return R1 and R2. Okay. Now, if I want the average of these two, so the average of these two is this R1 plus R2 divided by 2. This is my called as the expected average return, which is I can say as mu. However, if we have the returns, technically, if we take the average in this way, this is not correct. This is also called the arithmetic mean, which will not give the correct result. So the correct result will be based on geometric mean. And geometric mean, I think you all are aware of that formula, which is minus of 1, which is 1 plus R1. If I will add here R1 and 1 multiply by 1 plus R2. 1 plus R2. Okay. When I take the geometrical mean, this will adjust my volatility or the variation in my return. And this will provide the correct metrics for my average. So I can say that this mu minus adjustment of this is my geometric mean, and this u is my arithmetic mean. So log normal return, which is this factor ln of st divided by s naught, has the expected return which is log normally distributed and which is geometric mean. Very important point. Now, if I move into the second assumption, the second assumption is that it assumes that the risk-free rate is constant and which is known and which is always available for borrowing and lending. So we are assuming here the risk-free rate is a constant. The third point is that we are assuming that the trading is continuous. There are no breaks in the trading. The trading is continuous. Okay, this is the third assumption. The fourth assumption is very important.
the volatility of the underlying asset is constant and known. So, uh, what is volatility? Volatility is like I have the volatility this in my stock. So, BSM model assumes that the volatility factor is always constant. If the volatility factor is not constant, then the BSM model will not give the correct result. If the volatility factor is not constant, then we will not have a normally distributed returns, and the BSM model will give the incorrect result in that case. Another assumption is that the market are frictionless. There are no friction, like there are no taxes, no transaction, or there is no restriction on short sales or the use of short sale proceeds. So basically there are no friction in the market. That is also one of the assumption of BSM model. Another assumption is that it assumes that the underlying asset has no cash flow, such as dividend or a coupon payment. So for example, if I have a option and the underlying asset of an option, which can be a bond, if it is a bond, then it assumes that there are no coupon payments, and if it is a stock, then it assumes that there are no dividends distributed. And the last assumption is that the option valued are European option. So BSM model is only applicable for the European option. The European options are the option which can be only exercised at maturity. However, however, the American option can be exercised at any time. So the model does not correctly price the American option. So it only prices the European option, which can be only exercised at maturity. Okay. Hello. In this slide, I will explain you the pricing of call and the put option using the Black-Scholes-Merton model. So in this slide, you will see that there are complex formulas here. So this is the formula for call and this is the formula for put. So this mathematical equation is used to derive the price of call option and the put option. Now, I will not be explaining you how these formulas are derived in this presentation. I will be only explaining you the technical points and the fundamental points related to this formula, which will help you to develop more conceptual understanding of this pricing model. Before I start, I will give you some background of how the payoff of call option behave at maturity. So let's suppose we have a starting point here, which is 0. We are starting the option here and the option will mature at this point, which is t. Now the value of the option at this point t, we can say that it is based on this formula, which is s minus x. Okay. Or if this is not positive, this is negative, then it is 0. So we can say that the payoff of option is maximum of this. Okay, which is maximum of this. And let's suppose if the price of the stock is 12, and if my strike price, which is X, is 10, then at maturity, the value of the call option will be 2. Okay. Now the question comes here is, so this is the value of the option at maturity. Let's suppose if we want to find the value of the option before maturity, let's suppose at this point, okay, or let's suppose at this point, then how I will evaluate the value of option. So what this model does is that it identify what are the factors which will impact my price, and those factors are also called as the option Greeks. And you can see here in this formula, you will see that this time to maturity is a factor which will impact the option price at this point, or at this point we can also say that the volatility will also impact the price of the option at this point. So let's suppose if I have the volatility which is this, or if I have the volatility which is very high, for example this, then my option price will increase. So my point here is that to find the value of the option, we should know that what are the factors which will impact the value of the option, call or a put. Other factors are also like ND1, which I will explain, which is called the delta, like risk-free rate. So my point here is that what Black-Scholes model does here is that it will incorporate all these factors into this formula to find the value of the call and the put option. So it will account all those factors which impact the price of the option into a mathematical equation to derive a value. Okay. Now I will explain you the parts of this formula in detail. So when you look into this first formula, which is called option pricing, and when you look into this part, which is x multiplied by e raised to power minus RT. So what we are doing here is that we are doing the continuous compounding at a risk-free rate. Why we have to do the continuous compounding? Because X is a strike price which we will get at maturity. Okay, the value of X is at maturity. Okay, which is at this point. But if I want to price my option at this point, then what I have to do, that I have to discount that what is the value of my strike price at this point. So I am discounting that. And why I have used the exponential here? Because I want a continuous compounding. Okay, I will explain you what is continuous compounding. It is also important. You all know that what is the formula of compounding. So compounding, if you want to compound, what you have to do is that you have to use this formula 1 plus r raised to r divided by n, okay, and to the power t multiply by n. Okay, Now, if you want to compound at a half yearly rate, this n will become equal to 2. This n is the frequency at which you want to compound. And if you want to compound at a quarterly rate, then this n will equal to 4. But if you want to compound, for example, every second or less than a second, then what you have to do is that, for example, if n tends to infinite, if you want to compound at a very small time, which is equal to 0 approximately, then this formula will be equal to e raised to power rt. So it means that what you are doing here is that you are continuously compounding. So that is the word we have used here, continuously compounded. And when we are doing the continuously compounding, then we have to use the exponential function. And what we have done here is that we are discounting at a continuously compounded returns. Okay, what we are doing here is that, sorry, continuously compounded risk-free rate. So that is why we have multiply here with e raised to power minus rt. Okay, now I will explain what is this nd1 and nd2. So nd1 and nd2 is a cumulative probabilities. And what we are doing here is that we are taking the weighted average using these cumulative probabilities to find the price of the call option. So I am taking another example to explain this. What is this weighted average? So let's suppose let's suppose there is a game, okay, and you have to throw a dice. For example, you will get a 12 rupees if you get 6 as an outcome when you throw a dice. Okay, and if you will not get 6 when you throw a dice, then you have to pay 2 rupees. Okay, now if I want to find what is the expected value I will have from that game, then I have to use the probability as a weight. For example, if I will get 12, okay, if I will throw a dice and if I will get a 12, what is the probability for that? The probability of getting 12 is 1 by 6. Similarly, if you will not get 6, okay, if you will not get 6, then what is the probability for that? The probability for that is something around 5 by 6. Okay, now if you solve this expression, you will get the expected value. The expected value you will get. So my point here is that I have used this and this as a probability to find the expected value. Similarly, here we are using the nd1 and nd2 as a weighted value to find the value of the call option. Okay. Now, what is nd2? Suppose I have this distribution. Okay. And there is a point which is nd2 here.
So ND2 represent what are my chances that I will be in the money in the option, or my value of stock is, this stock is greater than my strike price. If my value of stock is greater than my strike price, only then the option will be exercised. Only then there will be a value of the option. Otherwise, it will have a zero value if it is less than the strike price, stock price. So this probability will provide the probability that, what is the probability that the stock price will be greater than the strike price. Okay. And we are doing the, we are using this as a weight for this element of this equation. Okay. Now what ND1 represent? The ND1 represent if my probability of stock is greater than my strike price. So this is the conditional probability. The conditional probability, then what will be the value of, what will be the change in the value of the call option with respect to the change in the underlying asset. We will also call it as the delta of an option. The delta of an option is what is the change in the value of the call option with respect to the stock change in the stock price. The stock price is the underlying asset of the option in this case. So we have used ND1 and ND2 as a weight, and we have calculated the weighted average using this formula, and we have evaluated the value of call option, which is C0. So for example, if I have a ND2, for example, it is 60%. Okay. And because we are using the conditional probability, which is ND1, ND2 is a probability, okay, when stock price will be greater than the strike price, and ND1 is a conditional probability if it is greater than, if it is greater than the strike price, then what will be the value of that? So for example, it will be 0.75%. It will be always greater than, because it is the conditional probability, it will be 0.75%. I'm just taking the hypothetical example. So in this way, like, we will apply these probabilities into this formula to evaluate the call option. Here you will see that D1, okay, the D1 is a factor where, based on which this normal distribution, cumulative normal distribution, we will calculate the value of the probability, and D1, which is equal to this formula. So in this formula, I think you just have to see the attributes in this formula. We have stock price, we have the exercise price, which is the strike price, we have the risk-free rate, we have uh, volatility, and we have time to maturity. The point I want to make here, let's suppose if you look into this, if this will increase, what will happen? So if you look into this, if this will increase, then my D1 will increase. Okay, my D1 will increase, and my, if my D1 will increase, my ND1 will increase. So if my volatility will increase, you will see that the value of the option will also increase. Okay.
In the same way, D2 is equal to D1 minus this volatility multiplied by root T. And this D2, with using this D2, we will evaluate ND2. Similarly, we can also evaluate the put option. Okay. So in the put option, we know that the value of the put option will be at maturity, which is x minus s, which is x minus s. So here also we are applying the same logic here. We are discounting this x in a similar way, and here we have used this 1 minus ND2 because we are doing the pricing for put option. Similarly, we have to minus this with S naught and we have to use the probability here, which is 1 minus ND1. So that's it from my side. Thank you.